My name is Miguel Angel, and I'm the project manager of Fab Engineering. Today I'll be introducing to you our team members as well as our project overview for the fall 2025 Civil Engineering Capstone class at San Diego State University. As I mentioned before, my name is Miguel Angel, and I was a project manager of the team as well as our stormwater engineer, Geotech assistant, and CAD specialist. Fernanda was the water and wastewater engineer, Angel Ruiz Murillo was our structural engineer, and Brenden was our geotechnical engineer. For the project overview, as stated in the request for proposal, San Diego State University is seeking a design-build solution for demolishing the existing parking lot of the existing university towers and constructing an enhanced 14,700 square foot reinforced concrete residential facility that is 9 stories tall and meets modern performance standards and sustainability goals. The proposed design includes updated utility systems and a new stormwater system, enhanced structural performance, and upgraded site features to support student housing needs. This will house 720 students. For our hydrological analysis, our goal is to ensure that the proposed University Towers East development meets the City of San Diego's stormwater standards, which requires treating 95% of annual stormwater runoff. The proposed conditions were designed so that all runoff from the new impervious surfaces is captured and directed into our treatment and detention system. This ensures that 95% of our stormwater is properly treated before discharge, meeting both Sdsu and city requirements. For our stormwater system, it is designed to collect, treat, and detain and safely discharge runoff from the site. Runoff first enters a 12-inch stormwater main, which conveys flow toward a centralized treatment path. All stormwater converges at the Contech inline CDS hydrodynamic separator, where the designed treatment flow of 0.23 cubic feet per second is processed. This removes sediments, debris, floatables, and pollutants to meet water quality requirements. From there, the treated water flows into a 4,000 cubic foot CMP detention tank, which provides temporary storage and helps control peak flows leaving the site. From the detention tank, water is routed through an 8-inch CMP pipe into our pump station. The pump provides 18.2 feet of head and an estimated 10.4 gallons per minute, pushing the water through a 2-inch cast iron force main. This force main enters a valve vault, which contains both a check valve and a gate valve. After the valve vault, water is discharged into a curb outlet structure. The curb outlet allows stormwater to pond temporarily and released by gravity into the street. This ensures a controlled discharge that protects Montezuma Road from flooding while maintaining compliance with City of San Diego drainage standards.
For SWQMP, we followed both City of San Diego and Sdsu standards. Our system is designed to treat 95% of annual stormwater runoff, using a Contech inline CDS unit to remove trash, sediment, and pollutants. Treated water enters a 4,000 cubic foot detention tank for flow control, and the overall BMP strategy ensures water compliance while allowing stormwater to safely discharge to Montezuma Road without causing flooding.
Hi, my name is Fernanda, and today I will be presenting the water study. The purpose of the study is to determine the building's domestic water demand, evaluate whether the existing utilities can supply sufficient pressure, and confirm whether additional pumping is needed to deliver water to the 9th floor. For the water study, we calculated our water demand to be 787.5 fixture units using the California Plumbing Code. Using the CPC demand curve, this corresponds to a peak domestic water flow of 181 gallons per minute. Based on the CPC friction loss charts, a 4-inch meter and a 4-inch service line were selected because they maintained acceptable pressure loss and flow velocity. The booster pump was sized to deliver approximately 181 gallons per minute at 150 to 160 feet of total dynamic head, which is required to provide adequate pressure to the 9th floor. For the sewer study, an 85% return factor was used to convert domestic water demand to wastewater generation. This value is commonly applied in multifamily and residential sewer design, where 80 to 90% of indoor water consumption enters a sanitary system as wastewater. We used an 85% return factor on the domestic demand, which produced a peak wastewater flow of about 153 gallons per minute. We confirmed that gravity flow is feasible based on site elevations and determined that a 6-inch sewer lateral provides more than enough capacity using Manning's equation. The building can drain entirely by gravity and no sewer pump is required. These standards do not allow an 8-inch lateral to be tapped directly into a 8-inch main due to it creating a significant backflow risk, potential for surcharge, and structural issues. As a result, the 6-inch PVC lateral was confirmed as the correct and compliant choice.
Our geotechnical findings showed that the first 6 to 7 feet of topsoil are highly expansive, with an R value under 5, which means they provide very little support. Because of this, we recommend removing the topsoil. Beneath that, we encountered stronger sands and gravels that are capable of supporting deep foundation loads. No groundwater was found on site, and overall, these conditions support our recommendation for a deep pile foundation system.
Hi everyone, my name is Angel, and I was responsible for leading the structural design for our project. My role focused on developing a system that could safely support the new building and still remain practical to construct. For this building, 9 stories in total, I selected a reinforced concrete structural framing system. Concrete was the best option because it provides strong seismic performance and aligns with current construction practices for mid-rise residential building. The floor system consists of 6-inch slab on grade and 12-inch elevated slabs, all reinforced to meet strength and serviceability requirements. Because this is a structural project in San Diego, seismic design governs many of our decisions. Our site falls under soil class C, which means we're dealing with very dense soil and soft rock conditions. Using this, I designed a system that complies with current seismic codes and required load combinations to ensure the building remains stable under both gravity and seismic loading. For the vertical system, I designed an 18 by 24 reinforced concrete column that repeats across all 9 floors. These columns were sized to carry the building's gravity loads efficiently while staying practical for construction. Based on the soil profile considerations, we're using a deep pile foundation system. This ensures that loads from the structure is safely transferred down to deeper, higher density soil layers. I designed the pile caps and reinforcement layout to avoid issues like puncturing and to maintain the required embedment. Now I'll quickly walk through the cost analysis for the main components of the project. Starting with demolition, we estimate a total cost of $1.1 million. For water utilities, $97,000. For sewer installation, approximate $13,000. For a stormwater system, including drainage improvements, piping, the required treatment components is budgeted at $341,000. The largest portion of the project is the structural work, which includes the foundation system, for an approximate $7.5 million. When we add all these scopes together and a 15% markup, the total project comes to an approximate $10.5 million.